All right, so now that we have some information about eigenvalues and determinants and how they're related, we can take a look at a couple of definitions here. I suppose we should probably do some actual problems first. So all that theory stuff about the determinants of the elementary matrices kind of help us prove information like information about the eigenvalues and stuff. So these are just let's go with a 2 by 2 matrix. Let's do number 5 as an example. So what was it asking? Characteristic polynomial. So this is not really an example of this last theorem here, but so if we're going to find an example, or if we're going to find the characteristic polynomial, remember the process. We're going to figure out what the determinant is of A minus lambda I. And remember that I is the identity matrix, so lambda times I would just be lambdas in the diagonal. And so your A minus lambda I would be the same thing as A, except for each element in the diagonal you would subtract by lambda. And then for 2 by 2, it's easy enough to find the determinant. We would do the diagonals minus the wings. So it's 2 minus lambda, 4 minus lambda, minus -1. Good to try to multiply things out so you can factor. 8 minus 6 lambda plus lambda squared plus 1. So lambda squared minus 6 lambda plus 9. And we want to find the thing. What? Well, this is a characteristic polynomial. We want to find out when this is equal to 0 because we want this to be, we want to find the solutions for the null space of this. Not the matrix A, but the matrix A minus lambda I. So this is -3. Oh, so when we find lambda, we're finding the numbers that would make this that would make it. We're finding the solutions of A minus lambda I. So remember where that came from. It's the vector x when applied to A is going to be the same as the vector, except that it might be scaled. And so the scaling factor is your lambda. That's the eigenvalue, and then the vector x is going to be the eigenvector. So the lambda that we're solving for here is eigenvalue. So this is a multiplicity two, and I included the word algebraic because we want to distinguish between this thing called an algebraic multiplicity and some other multiplicity. And then when we have this vector, we're going to plug that back into the original matrix, or this original A minus lambda I, and then find the vectors that would correspond to that. So I think that was the first exercise in this section, is to try to figure out if you have this thing called the eigenvalue, how do you find the eigenvector? So if lambda is equal to 3, then A minus 3I, or let's keep that as a matrix, is going to be 2 minus 3 is -1, and 4 minus 3 is 1. And so if you row reduce this, yeah. Yeah. So we have an eigenvalue, and then now we're about ready to get our eigenvector that corresponds to this particular eigenvalue. And so that vector is going to be, we have a free variable in x2. And so if you put that back, x1 is equal to x2, or minus x1 plus x2 is equal to 0, so x1 is equal to x2, right? So if x1 is equal to x2, then you have a vector x is equal to x2, x2, or a vector 1, 1 that can be scaled by x2. And then this is going to be your corresponding eigenvector. Yeah. In this case, maybe it is a coincidence. That's not always going to be the case. Which is 9. So sometimes we just call it x, sometimes we call it x sub 3, or whatever lambda is equal to. So if we get to those larger matrices where we might have 2 or 3 different eigenvalues, then we want to keep track of that. Okay? Then that means that that's the eigenvector that corresponds to the eigenvalue. It might mean something later. Be more meaningful, yeah.
So when we are declaring the eigenvector, we just drop any scalars, and it's just the vector.
Yes, because the scalar is just going to scale it longer, shorter, opposite direction, whatever, but we just care about the number. And in fact, remember, I think last time we got a 1/3 and 1/3, and we just say, oh, let's just call it 1, because we can scale it by something that makes that look nicer. Any other questions? I had a cool visual for eigenvectors, but I don't know if I can find it easily. I think we wasted enough time with my computer, so let's move on. Let's see if we could do another example with yeah. Well, these examples of 4x4 matrices are going to be, if you look at them, they're going to be easy, right? Yeah, so they're upper or lower triangular, so then your eigenvalues would just be, well, your determinant would just be the middle. Well, let's do one. 15's a good one. Because of special properties of determinants, and you know we have to find determinants to find the eigenvalues. The special properties of determinants will help us find the eigenvalues. So to find the eigenvalues, we find the null of this matrix A minus lambda I, and then we know that that's going to be the same thing as that matrix except for the diagonals. 4 minus lambda, 3 minus lambda, 3 minus lambda, and 1 minus lambda, and then everything else. And if you want the determinant of that, we already know that the determinant of an upper triangular matrix is just a product of the diagonals, then we don't have to worry. We can think about expanding, but you'll see that it's just going to be the product of the diagonals. 4 minus lambda, 3 minus lambda, 3 minus lambda, and 1 minus lambda. And if we set that equal to 0, it's already factored, right? And so everything that just comes out would just be each of these factors equal to 0. So each of these factors equal to 0, we're going to get our eigenvalues. 4, lambda is 3. This happens twice. And then lambda is equal to 1. So we have 3 eigenvalues. And then for each of these eigenvalues, we're going to be interested in finding the corresponding eigenvectors. Yeah. So this, because it's an upper triangular matrix, it's going to be invertible. The determinant's not equal to 0. It's invertible and all that. So that means that each of these columns are linearly independent, and then they span all of R4. So the eigenspace, we should probably expect the eigenspace to also put together should also span R4. And if there's 3 of them here, then that means one of them should have 2 eigenvectors associated with it. I hope. Let's see. Yeah.
It wasn't like upper or lower triangular. You want to make it into upper or lower triangular?
You can, but I think the best way is just to expand, because you're going to be carrying around something minus lambdas, and when you do that, then it gets a little bit trickier to solve for. All right, let's see if we can find, what are they called? Eigenvectors for each of these eigenvalues. So we have to treat each eigenvalue separately to find its eigenvector. So let's do lambda is equal to 4 first. A minus 4i, yeah. and then row reduce, and then find the null. So we have the matrix 4 minus 4, that's 0, minus 7, 0, 2, 0, this is going to be negative 1, negative 4, 6, 0, 0, 1, negative 1. Oh no, the negative 8. Negative 1. Right there. 0 and negative 3. So x1 is a free variable? Is it? It seems like x1 can be whatever it wants it to be, right? So let's see if we can continue to reduce. How should we do this? I don't know. I think it's going to be 1, 0, 0, 0. All right, well, let's see. This looks like it's going to be free regardless, so let's just work with the last 3 columns. I don't know. I feel like I probably want to switch the first 2. Minus 1, minus 4. Oops, let's put the 0 in. 0, minus 1, minus 4, and 6. 0, minus 7, 0, 2. 0, 0, minus 1, minus 8. 0, 0, 0, minus 3. So I did the row switch. And then multiply the first row by 7. Add it to the second row. Negative 7. Yeah, so that would make it positive 7. And that would cancel. So negative 28. Negative 40. And then this one will stay we'll do a switch. 0, minus 1, minus 4, 6. 0, 0, minus 1, 8. 0, 0, 28, negative 40. 0, 0, 0, minus 3. Minus 3. And then now, so we did a row switch, 2 and 3. And then positive 28. R2 plus R3. 0, minus 1, minus 4, 6. 0, 0, minus 8, or minus 1, 8. Minus 1, minus 8. 0, 0, 0. Well, big number. And then add 40 to 64. then you can just probably eliminate one of them. Just make the whole denominator, the whole bottom row equal 0. Oh, I'm out of room already. 88. So we can do one of those. Anyway, so this is going to end up. Let's just call it a 1 after a couple more reducing things. So if we're going to set this equal to 0, we're going to get x. So this is x3 is equal to 0, and x2 is going to be negative 8x3, so that's also going to be 0. Wait, sorry, x4, x3, and x2 is also going to be equal to 0. And then x1 is going to be free. So your vector here would be 1, 0, 0, 0. Does that make sense? I feel like we went through that the long way. Yeah.
What's like the largest number of eigenvectors you think that's what I
Probably 3. Yeah, it's 3 by 3, like a third degree polynomial. Yeah.
So I guess because you have pivot and every column after the first column,
Yeah, because there's going to be a pivot, and when you set that equal to 0, then all those variables are going to be equal to 0, except for that last one, or the first one.
you have one variable pivot, then whichever one is the other one can be 0 because they are pivots.
Well, we have to be careful, because if your non-pivot column is in the 4th row, then all the other variables will depend on that pivot, and so so we can't assume that there's 0. In this case, you can, because the free variable is in x1. All right. We still have 2 more eigenvalues to check, so let's go ahead and do that in the next page. Oh, this is where we're gonna set up the page. So we have 2 other eigenvalues. Let's do the eigenvalue 1. Probably where we should have started with. So for the eigenvalue 1, we're going to find the eigenvectors, vectors. And so what we want to do is we want to figure out the A minus lambda I business. And so 4 minus 1 is 3, minus 7, 0, 2, 0. 3 minus 1 is 2. And the last one is going to be 1 minus 1 is 0. So this is already in reduced form, right? Uh-oh. Here we go again. It's already in reduced form, so we have a free variable here. And then we have, this is x4 is free, so x3 is equal to Well, let's see, 2x3 minus 8x4 is equal to 0. That's going to be, bring the x4, the 8x4 on the other side, and then divide by 2 for x4. All right. And then the next one, we have 2x2 minus 4x3 plus 6x4 equals 0. So x2 is equal to, bring the x3 over and divide by 2. And so 2x3 minus 3x4. And then replace the x3. So that's 2 times 4 is 8. And then 8 minus 3 is 5. And then the last one, we get 3x1 minus 7x2, 0x3 plus 2x4 is equal to 0. We'll bring everything over and divide by 3. We get x1 is equal to 7/3 x2 minus 2/3 x4, and then x2 is equal to 5x4. So that's 35. And then 35 minus 2 is 33. Divided by 3 is 11. So all these will have an x4 in it. And so our solution for the null space, or we can find our vector, would be 11x4, 5x4, 4x4, and 1x4. So 11, 5, 4, 1 is going to be our eigenvector for the eigenvalue 1. Okay. Yeah.
So this is all just using the null space?
This is all finding the null space for each of these eigenvalues, So it's
not the null space the matrix?
Well, the null space of the matrix would be the null space for this. But this isn't that's not the original matrix. It's we want the null space of the A minus lambda I matrix, which is different from A. Yeah.
Is it similar to parametric vector form when you're like expressing it?
It's exactly the parametric vector form, except, when we get a free variable, we're going to call it T or something. But here, we'll just keep it at x4. All right, let's do one more. For lambda is equal to 3, that's our third eigenvalue. So the matrix that we have, A minus lambda I, should look like 4 minus 3 minus 7, 0, 2, 3 minus 3, and 3 minus 3 again, and 1 minus 3, negative 2. So I'll do a couple moves here just to get this this thing to go away. The bottom, I can multiply this by, I don't know, multiply the third row by 8. Oh yeah, I just multiply it by 1/4. Positive, negative, negative 1/4. R3 plus R4. That'll just get rid of that one. So we have 1 minus 7, 0, 2, 0, 0, minus 4, 6, 0, 0, 0, minus 8, 0, 0, 0, 1, 0. Thank you. I think it's already and reduced, right? Do we have any free variables? Where? X2? Is that the only free variable we have? Well, if we start solving for it, well, I think that'll help us clear it up a little bit. We have the first row is nothing, and then the second row get negative 8 x4 is equal to 0. So x4 is going to have to equal to 0. We have minus 4 x3 plus 6 x4 is equal to 0. So x4 is equal to 0, and then you solve for x3, so that's also going to equal to 0. And it looks like x2 is free. And then x1 is going to be zeros for the rest, and then positive 7 x2. I was hoping we get 2 solutions, but we only got 1. Anyways, so then your vector is going to be 7 x2, 1 x2, and then zeros for the rest. So for the eigenvalue of 3, we get an eigenvector of 7, 1, 0, 0. And that's it. Okay. So that's how you find eigenvalues and eigenvectors. And I think that's all. Well, that's not all, but. All right, let's take a look at some new definitions. Two vectors or two matrices are similar if you can find an invertible matrix P such that this is the case. In some textbooks, they actually use a different equation for similarity, and sometimes they use, let's see, P A equals PB. Is that right? No. AP. AP equals PB. Sometimes this is how it's defined in other books. They talk about an invertible matrix P so that AP is equal to PB. That means if you multiply A on the right side by this P matrix, and then you multiply B on the left side by that P matrix, then they're equal to each other. So two matrices are similar if this is true. Now this equation should be equivalent to these other two equations that are given here. If you just do the matrix multiplication with the inverses on the correct side, whether you're looking at it from the left side or on the right side. And so if I like take this equation over here and say I'm going to multiply by P inverse on the right side of both equations, I would have AP P inverse is equal to PB P inverse, and then this is equal to the identity, which is just going to say A is equal to PB P inverse. And it doesn't matter which way the inverse goes. You can put the inverse first, or you can put it on the left side of B, or you can put it on the right side of B, because if it's invertible, if Q is equal to P inverse, for example, then you have A equals Q inverse B Q, and so it's also going to satisfy the definition. So the theorem here says that if you have similar matrices A and B, then they should have the same characteristic polynomial. And you know, the characteristic polynomial is what helps us find the eigenvalues. And so, therefore, they must have the same eigenvalues. Say it again? Well, that's a good question. I don't. Or how would you even find B? Yeah. So. Well, you might be. Let's take a look at see if this thing has some problems that has stuff to do with that. They have a proof for that? Say it again? Yeah, whatever you, if you're stuck in a problem on the test. Okay, well, here's the thing, is that this leads up to the next section, and the next section focuses on the idea that what's so special, I mean, what kind of similar matrix would you want to compare to a matrix A? Say you're given a random matrix A, what kind of similar matrix would you like B to be so that you can compare it to A? Well, if your second matrix B is like an upper triangular, that would be nice, right? Because then we have a little bit more control. We know a lot more information about an upper triangular matrix if we, just by looking at it. We can find the determinant and all that stuff. So there's going to be something particularly special about the type of diagonal matrix that we're looking for. And the type of matrix that we're looking for that's similar to your original problem matrix is going to be a diagonal matrix. What's a diagonal matrix? So, if we can find a matrix similar to A that has a special feature, then we can have more information about, we can find out more about A by just looking at that other matrix. And so the matrix that we're looking for is a diagonal matrix. So what we have here is a diagonal matrix is going to have whatever you have in the diagonals and 0 everywhere else. So it's not just an upper triangular matrix, not just a lower triangular matrix, but actually have zeros everywhere else except for the diagonal. Yeah. And so if you take a look at that last theorem over here, it says they have the same eigenvalues. If you have two matrices that are similar to each other, they're going to have the same eigenvalues. Well, we know that for an upper triangular matrix that the eigenvalues are just going to be the diagonals. And here, it's not just an upper triangular, it's an actual diagonal. So these will end up being, I think that's in the next statement here. Well, before I put that there, let's get a different color. So the eigenvalues the elements in the diagonal are the eigenvalues. So you can actually get the eigenvalues just by looking at the diagonal matrix. Okay? What if we turn that thought around? So what I'm saying is that if I give you a diagonal matrix, you can just look at it and say, oh, the eigenvalues are going to be whatever the diagonal is, right? So what if I turn that around and I say, okay, this matrix A has eigenvalues 1, 2, and 3. Can you give me a matrix similar to this that's a diagonal? Then you would just tell me that the matrix is going to have a diagonal 1, 2, and 3, and zeros everywhere else. And they would be similar. So that's our first step, is to try to figure out how to find that diagonal. And the way to find that diagonal matrix is by finding the eigenvalues of A. Okay? So now Erica had a question about what's that invertible matrix P. So if you can find the similar matrix D, but now you have to find a P. And then that P can be found by this thing called the diagonalization theorem. The P will actually be made up of eigenvectors in columns. So it's going to be a matrix of eigenvectors. Well, the diagonal will be the eigenvalues. And then remember that for this to be similar, we need an invertible matrix P to multiply on either side. And it turns out that matrix P that we're looking for is going to be made up of the eigenvectors from the eigenvalues. Yeah?
So P is the B matrix. Is this the diagonalization?
Yeah, so B, the one that we're talking about, the B matrix, they're just being kind of generic and general about that. But B is not going to be of any use to us if it doesn't have any special properties. And so it's just saying that this is a definition of similar. So they first introduced similar, they didn't say anything about B. B can be a lot of different matrices. But what we're interested in is a special matrix that's going to have a special feature, and the special feature is that it is a diagonal matrix.
So if it's not a diagonal matrix, then it's not really important.
Then it's not. I mean, it might be important for something, but it's not.
It is.
Yeah. Andrew? No. All right. So matrix A is diagonalizable if A has n linearly independent eigenvectors. In fact, that A is going to be equal to P, D, P with the diagonal matrix D, if and only if the columns of P are n linearly independent vectors of A, eigenvectors of A. Say it again. If your eigenvalues have multiplicity, then we should hopefully find eigenvectors that have that have multiplicity of the same. I think so. All right, let's see if we can find some examples here. Oh, here's an algorithm. And a couple more theorems. So the step-by-step process of diagonalizing, this is called diagonalizing a matrix, where we get a matrix and we want to find a diagonal. First, we have to find the eigenvalues, because that's what the diagonal is going to be made of. Next, we have to find the eigenvectors for each of those eigenvalues. And then you're going to make, out of those eigenvectors, you're going to make your matrix P. And if they're linearly independent, we know that that's going to be invertible. And then form your diagonal matrix in the same order corresponding to the eigenvectors. So remember that each eigenvector corresponds to an eigenvalue. So you just want to make sure that they're going to be in the same column. Like if you have eigenvalue 1 in the first column, then you should have the eigenvector for 1 in the first column of P. Yeah. How you set up your eigenvalues doesn't matter as long as you set up your eigenvectors in the same way. You can choose any order you want. Yeah.
I mean that sincerely. It seems like this would be really helpful to help you find eigenvalues and eigenvectors, but it seems like we're doing this based on making the very
Oh, we're doing this to, we need to find the eigenvalues and eigenvectors to be able to do this.
Okay. So what do you think?
I don't know. It'll just look cool. Oh yeah. Just like that. Let's see. If you have A and you want to raise it to the 15th power, you'd have to like multiply that 15 times. Okay. It turns out that if you have 3, 0, 5, 0, 0, 5, 0, 0, 0, 2, if you multiply this 15 times, first of all, if you multiply it twice, this is a generic diagonal matrix. If you multiply this, you're going to get 9, 0, 0, 0, 25, 0, 0, 0, 2, 4. So it turns out that if you take a diagonal matrix to the power, it's like taking each diagonal to that power. So that's a nice property for diagonal matrices. So now, yeah, if you want to take a generic A to the 15th power, if you can diagonalize this P, D, P inverse, raise that to the 15th power, that looks long, right? But what is this equal to? This is equal to P, D, P inverse, P, D, P inverse. $15 times, right? And you can do the associative property P D D P inverse P D P inverse, and you can group all the middle P inverse times P business. You see what's happening? So they're all going to go away, and then we just have P D to the 15th power P inverse. And so what happens there is that all you have to do is take your diagonal to the 15th power and then multiply it on the left by P, multiply it on the right by P inverse. So that's 2 multiplications instead of multiplying A 15 times. So that would be 1.
Why are we going through this?
Because this thing is not equal to P inverse. You can't, it's not commutative, right? You can't switch the order. All right, so we didn't get to diagonalize a matrix. Boy, that took longer than should have. Yeah, we could do that next time. All right, so next time we'll do this. You know what? Maybe I'll do a video and then you guys can look at it at home so that by the time you come back here on Monday, you know how to diagonalize a matrix already. Or you guys could do a worksheet. Yeah, we'll do a flipped classroom.
I'm not sure.